To build a single modern city, forge its steel backbone, and feed its population, you need millions of tons of raw earth. Long before a smartphone or a car rolls off an assembly line, the raw materials to make them have to be extracted from the ground and moved across the globe. This is the domain of dry bulk cargo. We're talking about unrefined commodities like iron ore, coal, and grain. Because these materials are needed in such astronomical volumes, packing them into individual shipping containers or wooden crates would be a massive waste of space and packaging. They have to be shipped loose, poured by the thousands of tons. These commodities originate in places far removed from where they are consumed. Iron ore is torn from vast terraced pits deep inland in Australia and Brazil, while coal is mined across remote regions to feed distant power grids. Satisfying global demand requires extraction on a planetary scale. Moving mountains of material across oceans required engineers to rethink maritime transport entirely. They had to invent a colossal machine, specifically designed to swallow up the earth and carry it whole. Prior to the 1950s, moving raw materials was a brutally slow process. Dock workers manually shoveled cargo into heavy burlap sacks, stacked those sacks onto wooden pallets, and hoisted them down into the tight confines of traditional cargo ships. As global crude steel production climbed toward the hundreds of millions of tons, the old ways collapsed. A team of men moving sacks by hand couldn't keep pace with a blast furnace that never sleeps. The time spent sitting at the dock became more expensive than the voyage itself, making manual labor the primary bottleneck of industrial growth. Architects stopped trying to fit bulk materials into the multi-deck skeletons of traditional cargo ships. Instead, they began engineering the ship around the cargo. They designed the vessel to be a single, unobstructed steel cavern, where gravity, not muscle, did the work of loading and unloading. This created the modern bulk carrier. Every interior angle and structural reinforcement is calculated to maximize volume and minimize turnaround time. In this design, form follows function, with a singular focus, moving the maximum amount of mass at the lowest possible cost per ton. To maximize internal volume, a bulk carrier abandons the multi-level decks found in passenger or general cargo ships. It features a single main weather deck with massive steel hatch covers that open directly to the sky, exposing caverns that reach all the way down to the hull's reinforced inner bottom. Look at a cross-section of the hold, and you'll notice a highly specific geometric design. The interior is not a perfect rectangle. There are thick, triangular compartments running along the upper corners, known as topside tanks, and the lower corners, called hopper tanks. These angled tanks serve two critical functions. First, when sailing empty, these compartments are pumped full of seawater ballast. This extra weight drives the ship deeper into the water, lowering its center of gravity so it remains stable in rough ocean swells. Second, when it's time to load, the water is pumped out and the cargo is poured in. The sloped surfaces of those lower hopper tanks act like a funnel, forcing loose, granular material to naturally slide toward the dead center of the hold. This geometry is a survival mechanism. If millions of pounds of loose grain or coal were allowed to shift from side to side in a flat-bottomed room every time the ship rolled, the vessel would capsize. The angled tanks lock the cargo's mass exactly where it needs to be. Bulk carriers are classified by their deadweight tonnage, or DWT, the total carrying capacity of the ship. But naval architects don't just build these vessels as large as they want. Their exact dimensions are strictly dictated by the geographic bottlenecks they must pass through. The smaller handy-sized ships, carrying up to 40,000 tons, are built to squeeze into shallow, regional river ports. Step up to the Panamax class, and the ship's length and width are pushed to the absolute maximum limits that can scrape through the locks of the Panama Canal. Then there are the Cape-size vessels, routinely hauling upwards of 150,000 tons. These ships are too large for the Panama or Suez canals. To move iron ore from Brazil to Asia, they must sail around the stormy continental tips of the Cape of Good Hope or Cape Horn. At the extreme high end are the ultra-large ore carriers, which exceed 400,000 deadweight tons. These are some of the longest machines ever built, deployed almost exclusively on fixed, long-haul routes, connecting major mining conglomerates with massive steel producers. As these ships push the boundaries of scale to drive down the cost per ton, they trade away their geographic flexibility. The largest bulkers on Earth are essentially trapped, able to dock at only a handful of specialized ultra-deep water mega-terminals around the globe. When a giant, gearless bulk carrier arrives at one of these terminals, the ship itself does no lifting. It relies entirely on a sprawling ecosystem of shore-based infrastructure, a maze of conveyor belts, stackers, and heavy port machinery designed to empty the vessel. Massive grab cranes lower mechanical clamshell buckets deep into the hold, taking a multi-ton bite out of the cargo with every pass. In more advanced ports, continuous ship unloaders lower bucket elevators straight into the pile, extracting rock and coal in a relentless, uninterrupted flow. Not every ship visits a mega-terminal. Smaller, geared bulk carriers are outfitted with their own heavy deck cranes. This makes them entirely self-sufficient, allowing them to deliver crucial fertilizer or grain to remote developing ports that lack expensive dockside machinery. Whether relying on the port or their own cranes, the commercial pressure is identical. A ship sitting at the dock is burning cash. Generating profit requires a violent, heavily choreographed race to load, empty, and return to the open ocean as fast as the laws of physics permit. Once fully loaded and back at sea, the massive scale of the cargo goes from being an economic asset to a terrifying physical liability. Across thousands of miles of open water, the ship endures the constant, heavy pounding and high-frequency vibration of ocean swells. This vibration can trigger a lethal phenomenon known as liquefaction. If a high-density cargo, like nickel ore or iron ore fines, holds too much hidden moisture, the constant shaking forces water to the surface. What was loaded as solid rock suddenly behaves like a sloshing, heavy fluid. When the ship rolls into a wave, that liquefied mass surges to one side of the hold and stays there. The vessel's center of gravity is instantly destroyed. Trapped under thousands of tons of dead weight leaning heavily to port or starboard, a bulk carrier can capsize with terrifying speed. Even without liquefaction, the crew faces relentless secondary threats. Highly acidic cargoes slowly eat away at the hold's steel plating. Microscopic coal dust creates severe explosion risks, and the massive steel hatch covers must maintain a perfect watertight seal against the immense pressure of crashing waves. These vessels are far from simple, passive containers. They are highly engineered survival mechanisms, locked in a continuous, high-stakes battle against the brutal physics of their own payload. Through extreme scale and unyielding structural design, the bulk carrier operates quietly in the background of our global economy. It is the unglamorous, invisible backbone of modern industry, quite literally moving the Earth to build civilization. But what happens when the raw materials powering our world can't be poured down a chute? If this is how we move solid rock, what kind of machine is required to safely transport millions of gallons of highly explosive fuel? That requires an entirely different breed of giant.